Okay, we are going to talk to you about Cramer's rule. So Cramer's rule is the idea of using determinants sort of as a method of solving systems. We know a couple of ways to solve systems already. We know we can do it by row reduction. And so we're going to look at this alternate method. There are going to be times when Cramer's rule is useful, times when Cramer's rule is less useful. I'm just going to set up here. This is kind of why Cramer's rule works. I don't want you to worry about taking too crazy notes for this part, but this is just sort of where it comes from and why what we use really works. So if I was just using, for example, this is some sort of general two variable system, right? Some x's plus some y's equals some number. You know, some x's plus some other y's equals some other number, right? So we've got two equations with two variables. So you can imagine if we were going to try to solve this by elimination, one thing that we could do, like to eliminate the y's, for example, right? So we could multiply the first equation by, say, like negative b2, and the other one by, you know, b1 or vice versa, right? So the idea would be to eliminate the y's. Let's just, let me multiply by positive b2 here, and I'll multiply by negative b1 here. Okay, so if we did that, you can see what we would get. We would get a1 b2x plus b1 b2y is equal to c1 b2 here, and then down here we would get negative a2 b1x minus b1 b2y. There's the elimination there, right? Is equal to negative b1 c2. And then if we add these together, eliminating the y's, that would add to 0. We would get a1 b2 minus a2 b1 all times x, right, is equal to c1 b2 minus b1 c2. Then to solve for x, we would divide by this, right? So x would be equal to this thing divided by a1 b2 minus a2 b1. Okay, and so what you start to notice here maybe is if you think about the coefficient matrix for this, so think about this coefficient matrix as matrix A, what we would have is A1, B1, A2, B2, right? The way we've set it up here at least. And so if you think about what is going on here, you might notice what this is, right? If we look at this matrix and see that, and thinking about determinants, A1, B2 minus A2b1 is actually the determinant of this matrix here. Okay, so this is actually the determinant of matrix A. And you might notice that this also looks like a determinant as well of some sort of 2 by 2. And what it would be actually would be if we took the, so you notice we've got the same statements here with B1 and B2, but you can see C1 is swapped in for A1, C2 is swapped in for A2. So what this is really, this would be the determinant of A with the sort of the C column, the C entries replacing the A entries, right? So the C's replacing the A's, those entries, okay? And so the idea of Cramer's rule, I won't go further. You can do that and see how we would also solve for y. But the idea here is really we find the determinant of this coefficient matrix and we base our solutions for the variables off of the determinant of that coefficient matrix, and then also the determinant of the coefficient matrix, but with your sort of your right-hand side values swapped in for one column at a time. Okay, so let's say we, you know, our 2 by 2 case, so if we have some sort of ax plus by equals, let's just call it f, I guess, for now, and then cx plus dy is equal to g. Okay, and so if I look at, you know, my coefficient matrix is ABCD. Okay, and most texts will go ahead and they'll look at the determinant of this. So the determinant of the coefficient matrix, we're going to go ahead and call it capital D. Okay, so capital D will be our determinant of the coefficient matrix. And then the idea here is that x is going to be this capital D, the determinant, but with the FG thought of as a column replaced into the x coefficients of the matrix divided by the normal determinant there of the coefficient matrix. And y is going to be the determinant there, but with the FG as a column substituted in for the y coefficients BD here. So we'll call that D sub y. Okay, so x is going to be equal to the determinant with the right-hand side plugged in for the x column, that determinant, divided by this regular just determinant of the coefficient matrix, and then similar thing for y here. So let's just work through maybe an example, and we'll sort of see what's going on with that. Okay, so for an example, let's say we're trying to solve 12x plus 3y is equal to 15, and 2x minus 3y is equal to 13. Okay, so the first thing that we'll do is just find the coefficient matrix A. Okay, so A is obviously 12, 3, 2, negative 3, right? So D is going to be our determinant of A, and we know what that is. That's going to be 12 times negative 3, so negative 36, minus 3 times 2, the other diagonal, which is 6. So we get negative 42 for that determinant. So that's going to be our capital D. Capital D is negative 42. To find D sub x, what we'll do is we will actually take our coefficient matrix A, and in place of the coefficients in the x column, so the 12 and the 2 in this case, we're going to swap the right-hand side values in order. So 15 and 13 go in the what we think of as the x column for the coefficients, and then we'll leave the other column the same. Okay, so if we go ahead and do the determinant of that, we'll get negative 45 here, minus, we'll get a 39 there, so that is negative 84. And then for our D sub y, that will be the determinant if we take the 15 and 13 and replace the y coefficients, so the 3 and the negative 3 are going to get swapped out for this one. And we'll keep the original of the other column. Okay, so in D sub x, we're plugging the right-hand values in for the x column coefficients. For D sub y, we're plugging it into the y column. Okay, so here, this is going to be 12 times 13, which is 156, minus 2 times 15, which is 30. So we get 126 there. And so I have, my regular d, I have dx, dy, so I should be able to do this. So x is going to be dx divided by d, which is, what is that? Negative 84 divided by negative 42, which is 2, so x is 2. And then y is going to be d sub y divided by d. Don't think of these as derivative notations, right? This is just determinants with some columns swapped in for some of these. This is 126 divided by the negative 42, and in that case, that actually turns out to be negative 3. Okay, so now I wouldn't do this particular system with this method because obviously I see a plus 3y, a negative 3y. I don't even really need matrices to do this, right? I could just add these together right away. So there are going to be times where you'll use this and this will be okay, and sometimes you won't want to use this. This is just a generic, example that I'm giving you just so you can work it out. Okay, let's do one more maybe, just as a good example here. So example of another 2 by 2, let's do x plus 2y is equal to negative 11, and negative 2x plus y is equal to negative 13. Okay, so if we do this, then let's think about capital D is going to be the determinant of these coefficients as they are, right? 1, 2, negative 2, and 1. So if we do that, that's going to be 1 times 1 is 1, minus a negative 4 there, plus 4, so that'll be a determinant of 5. And then let's go ahead and do our d sub x and d sub y. So d sub x is going to be the determinant of, so we will keep the y coefficient column in. We'll go ahead and take the negative 11 and negative 13 and swap those in for our x coefficients. Okay, so d sub x is this. So here we'll get negative 11, be careful here, plus 26, so that's 15. And then d sub y will be the determinant with the negative 11, negative 13 swapped in the y column, and we'll leave the original x column. So here we'll get negative 13. And then here we'll get 22, but then minus, so minus 22 gives us negative 35 there. Okay, so x is d sub x over d, which is 15 over 5, so that's 3 in this case. And then y is d sub y over d, which is negative 35 divided by 5, which is negative 7. Okay, so 3 for x, negative 7 for y. Now again, this is something that's easy to do by hand. You could certainly, do this with any method and not just this being the best method for this. This is another way to solve these. Now, some ways that you maybe wouldn't want to choose this, I think would be, simple things where you can just kind of do the elimination real quick by hand and go. I think that would be great. So these two examples maybe not the best choice for solving by determinant. What we might want to do, though, is if we have something that would be really nasty, maybe, at least, with the arithmetic, if you have something like 39x plus 14y is equal to 11, and you have, 7x minus 23y is equal to 9. So, sort of think about, because these numbers maybe aren't super friendly to get easy common multiples and just do it real quick with your arithmetic. The idea here is that, okay, well, if you eliminate, you're going to be using big numbers and you'll get big numbers. You'll get some sort of, maybe even you get a fraction, right, for x or y. Then you're going to have to take that fraction that's not friendly and plug it into stuff that already kind of has weird numbers. And so if you're going to get, complicated fractions for x and or y, and then having to plug those back in and get stuff, that may not be the efficient way to do that. And so the Cramer's rule might be a better candidate for this one. I think this is a good Cramer's rule example here. That would be just fine. Another thing about Cramer's rule, and think about if I don't want to solve the whole system, let's say I just need x or I just need y, as long as I could, so if I want to know y only, then I just need to find d sub y and d, right? I don't need to do much else. So that's a quick just, this minus this for one of these and this minus this for the other one. And maybe that's a shorter thing. If you don't need to solve the whole system, you just need one of the values. Okay, so a couple of things maybe to think about when using, beyond this course, deciding whether should I be using Cramer's rule, should I not be using Cramer's rule. Let's do an example for, like a 3-variable system. So if you had 3 variables, same idea, right? So, we'll have the determinant of the coefficient matrix D. D sub x is still going to be, you're going to take your right-hand side, you're going to swap it in for the x column, find the determinant. D sub y you'll have, and then you would also, I guess, if it's a 3-variable, you might have d sub z, right? Okay, and so that's going to be, you take the right-hand column, you put it in for the z column, right, and do the determinant. You might not be using the alphabet, so we might be doing, d sub x1, d sub x2, d sub x3. You've seen in a lot of the videos, and in homework sometimes we use, x, y, z, sometimes we use x1, x2, x3. This being a little more common in linear algebra, this being a little more common in like precalculus and things like that. Okay. So let's do an example, just work through one. Now you can tell these are going to be more tedious just because they are 3 variables, right? And so doing the determinant is going to be a bit more work. So really when you get 3 variable and above, Cramer's rule, I would say you probably only want to use this computationally, especially by hand, if you're only solving for a specific variable. Okay, I'm going to go ahead and solve the entire system just so you can see one done. So if we go ahead and set up our, D here is going to be the determinant of, if I do this 1, 1, negative 1, 3, negative 2, 1, 1, 3, negative 2. I can tell this is where people start skipping in the video. So here I'm just going to expand the first row. So that would be 1 times 4 minus 3. This is assuming you know how to do determinants. If you don't, you need to go back and look at last week's video, but I'm not going to spend a ton of time doing this here. So this would be 1 times -6 minus 1. Minus 1, it's in a positive spot, but it's already a -1. So here we'll have 9, that would be plus 2. And so then we end up with 1. -1 times -7 would be plus 7, and then we'd get minus 11 here. And so that's going to be -3 for d, okay? dx, so dx is going to be determinant, but with the x, the 1, 3, 1 column swapped out for the 6, -5, and 14 that's on the right side, right? So in the x column, I usually write that first. Sometimes people, they just, write the wrong thing in the wrong place. So write it in first and then go back and fill in the rest so you don't make an oops, It happens all the time, right? Okay, so dx here. So I'll just expand the first row. So 6 times 4 minus 3 again. Minus 1, this is in a minus spot. So here now we have 10 minus 14. Here we have minus 1. It's in a positive spot, so times positive 1. So here now we have -15. Careful here, this would be plus. So -15 plus 28. And then here, this is 1, so this is 6. -1 times -4, so that's plus 4. This would be 13 in here, so we'd have minus 13 there. So then 10 minus 13 would be -3. So we can already see, right? Like if you didn't need anything else, you could say x is d sub x over d. We already know that's, in this case, -3 over -3, so we know this is 1. I'll keep going, though, to make sure that people are okay. So if I'm doing d sub y, then I'm going to take the original d here, but I'm going to be swapping out the y column for the 6, -5, 14. So 6, -5, 14 is going in here. And then the 1, 3, 1 is staying. And the -1, 1, -2 is staying. So expanding my first row again, I'll do that. So 1 times, here we have 10 minus 14. The 6 is in a minus spot, so minus 6 times -6 minus 1. Plus -1, so that's minus 1. And then here, we would have, this would be 42, minus a negative would be like plus, so 42 plus 5. And then here we'd have 1 times this is -4, this is -7 times -6, so that's positive 42 there. This is 47, so that's minus 47. Okay, so here we would have, however you want to do this, this ends up to be -9, I believe. So we can already see then that y is going to be dy over d, which is -9 over -3. D up there, right? Which is 3 for this one. And so then dz, scroll down just a little bit, enough that we have room here. So dz, we're going to take that 6, -5, 14, put it in for the z coefficients, right? So keep the original x column coefficients, the original y column coefficients. And we'll do that, okay? So here, expanding first row again, we'd have 1 times, this would be -28, minus a negative would be like plus, so that'll be like plus 15. So -28 plus 15. My 1 is in a minus spot here, so -1 times, here we'd have 42 minus -5 would be like plus 5, so 42 plus 5. 6 is in a positive spot, so plus 6 times Crossing that out, we'd have 9 minus -2, which would be like plus 2. Okay, so then here 1 times this is -13 here. This is 47 in here times -1, so minus 47. Plus, and then here this is 11 times 6. So if we do all of this here, notice you have -60 here plus 66, so that's going to end up being a positive 6. And then your answer for z is going to be d sub z, right, divided by d. Remember our original d doesn't change for any of these, so that's -3 here. This one's 6. 6 divided by -3, we should get -2 for this one here. Okay, so that's an example fully worked out. Cramer's rule, once you kind of get the hang of it, determinant of the coefficient matrix is always your denominator in each of these statements here. And then just making sure that you swap in your equal to values, making sure you swap the right side in for the correct column, and basically, not making arithmetic mistakes. So a lot of this we would do by computer, of course, but just making sure that we understand how Cramer's rule works, and how it goes about actually computing using that idea that we started with back, when looking at what would happen when we did elimination. We get these kind of statements here. Okay, so that is Cramer's rule. You should be able to apply that. Now, of course, one thing we'll probably notice is that these solutions are going to depend on capital D not being a particular number. If all of these solutions are, something divided by capital D here, this is only going to work if capital D is not 0, okay? So if the determinant is 0, that's going to be one of those weird cases, okay? So if the determinant of A, or what we called in this video capital D, equals 0, then what happens is then, actually a lot of things happen, but with solving systems, then the system does not have a unique solution, okay? Has no unique solution. Now, no unique solution could mean two things. It could mean that it has no solution, period. So either no solution, period, or it could have infinitely many solutions, right? Infinitely many solutions. But you don't get a solution of something like x is 4 and y is 9, z is 12, right? We get either infinitely many solutions, or we get that it's an inconsistent system, what we call no solution system sometimes. Okay, so for your system, I would say always do capital D first, because what you don't want to do is, so we want to find capital D first. What you don't want to do is go in and find what is d sub x, d sub y, d sub z. You get to capital D, you do that last, and then you realize it's 0, and then you go no solution. You did a ton of determinants that you didn't need to do just to find out that, there is no unique solution, and Cramer's rule will not allow us to solve the system. We've got another video talking about finding some inverse matrices, also using determinants a little bit to find the inverse of a matrix. So that's our other big video for the week. Check that out when you get a chance. And those two videos should help you solve your homework problems. All right, take care, everybody.